I've chosen 3 more problems in real analysis to look at. So the first one here is about sequences and series. We're given a sequence of real numbers. Every term of the sequence is between -1 and 1, but not including -1 or 1. And we're told that the series an over n converges, and that the series of an over 1 plus an also converges. What do we want to show? We want to show that this is enough to claim that the series of an to the 4th converges. So this means that you take a1, raise it to the 4th, add it to a2, raise it to the 4th, plus a3 to the 4th, plus a, whatever, you know how series work. Anyway, so this is a relatively short proof. It was, I think that this was on a qualifying exam in January of 2020. So it's a couple years old now. And the proof is pretty short, but there's some steps in here I'm a little bit queasy on. And maybe you'll see why I'm queasy on it. So first we're going to make some notation. We're going to let alpha be equal to the first sum and beta be equal to the second sum, which is fine. I'm just giving it a name. We know the series converges. If we take the difference of the two, meaning that we take this and subtract this, because they're convergent, we can subtract them term-wise. So we have an subtract an over 1 plus an. And then if you rearrange that algebraically, you should get this term listed here. Okay. Now this series converges because it's equal to alpha minus beta. And we want to make the claim that the series of an squared converges. And we can show that this converges using this series here. Now this sum, we are told, converges, which means that the sequence an has to tend towards 0 versus sufficiently large n. Okay, so here's kind of where the hand-wavy stuff comes into play. I always like the hand-wavy stuff. We know that since this sequence tends towards 0 as n gets large, we know that this will tend towards 0 and this will tend towards 0, but you have this 1 downstairs. So the denominator kind of behaves like 1, whereas the top still behaves like an squared. So we know that for sufficiently large n, this fraction behaves like an squared. And since this series converges, we can show that this series converges. And I have a comment on this there, but let me just finish the final sentence here and then talk about it a little bit later. As an to the 4th can be rewritten as an squared times an squared, and we know that this series converges, we can use this fact together to show that the sum of an to the 4th converges. Okay, so it's short, but the reason it's short is because there's a lot of hand-wavy stuff going on here. For example, the first part that makes me queasy is we have this alpha minus beta up at the top. It's not super evident to me at the moment why we're able to subtract term by term, because we're told that the series converges, but it doesn't absolutely converge. I don't really think that makes a difference. I think it's just a matter if the sequence doesn't diverge is the most important thing that we care about. Because otherwise, how can you say that the difference of the limits is equal to the sum of the difference of terms pairwise? You know what I'm trying to say? How do I know I could do a1 minus a1 over 1 plus a1? And then plus a2 minus a2 over 1 plus a2. What I'm saying here is that it matters a little bit how you arrange the terms. Although I think since the series converges here, we don't have to worry about that too much. So that part I'm not super scared of. I think this is just me needing to go back over my definitions of sequences and series. Now, this next line, no problems with. Obviously, if that converges, the sequence has to tend towards 0. I also don't worry too much about what's going on here. meaning that we know that the an kind of disappears when you get really, really small. It behaves like 1, and the top is still your an squared. But the thing that does concern me a little bit is that there's not really a whole lot of rigor here. Because this wavy sign here, well, I mean, what does that really mean? It's a matter of showing that, oh, it's the same thing that happened with that one problem I did in episode, I want to say it was 3, where I did an old qual problem. So there are heuristics here, if you want to use that word. But depending on who's grading it, this may be enough, although it probably should be a little bit more rigorous. But it's the idea, right? You can compare these two terms here, and since this guy converges, this guy can converge. And then the last term I don't have too many problems with, but I mean, oh, okay, okay. So I was a little bit concerned with the last sentence, but then I remembered that my ANs are between 0 and 1, and since AN squared is bigger than AN to the 4th, and that series converges, then this series should also converge as well. And this term is non-negative, as well as this term is non-negative. So it's a nice little problem, I think. I just wish I had more details for this step here. But anyway, that's more or less the idea. Okay, second problem. Let f be an L1 integrable function on the interval from 0 to infinity. We want to prove that there exists a sequence that diverges, so increases without bound, I should be more explicit, such that the limit of xn times f of xn equals 0 as n tends toward infinity. Alright, so this problem I got off of the internet. I just found it on some website with the solution because I was looking for stuff to basically practice problems like this for my analysis qual. So the proof is pretty short, but it requires a little bit of, just a tiny bit of thinking. So it's a little bit harder than the last one. So the idea here is that we pick a c, some constant c, and we want it to be the limit infimum as x tends toward infinity of this function here. So we take the absolute value of fx and multiply it by x. So x increases without bound. And we know that fx is integrable, right? Because we assumed it was on this interval. So we know that it has to decrease, right? Well, do I know that it has to decrease? I think the limit of fx has to tend towards 0 in order for it to be integrable, or else it doesn't make sense as x grows large. There has to be some sort of integrable majorant. So you can let c be that guy. And if c is equal to 0, then we know that such xn exists. Why? Oh, because it's defined to be the lim infimum, right? It's this guy, which looks like this guy. That part's not too hard to see. You can just pick elements of your sequence, and then it'll work if c is equal to 0. But the issue is what happens when c is not equal to 0. So notice that x increases without bound, and we're taking the absolute value of f. So we know that c is non-negative. So if c is strictly positive, what can we say? Well, I believe this result here has a name. I can't remember the name of it, though. It's like... oh, shoot, it's going to bug me now. Let me look up in my math book here. Local positivity, I think. More or less. Yeah. I think it's called local positivity. So I'm looking at this theorem right here from this book. I think that's applicable in this. Well, I mean, it's not exactly as it is written in that book, but it's very similar in formation. So what does it say? It says that for sufficiently big x, so we can find an a positive where we take x larger than a, we know that x times the absolute value of fx is strictly greater than c over 2. Yes, so that makes sense. Now what can we say about the integral? So we assumed that f was L1 integrable over 0 to infinity. So we know this integral is, it exists. And we know that this integral has to be greater than or equal to the same integral, except now you're starting at a, which makes sense that this would be smaller because a is strictly positive. So you're integrating over a smaller set. Now, the absolute value of f is strictly greater. In fact, I probably could have written that here. Strictly greater than c over 2x. And I didn't include my dx here or dm, but it doesn't really matter too much. And I know that from dividing this x off to this side. I'll get c over 2x. But this integral diverges. Because this is c over 2, that's a constant. So it can be pulled out. And then I have the integral of 1 over x dx from a to infinity. But that integral definitely diverges. So we've bounded this guy below by infinity. And that would contradict our original assumption. So we know that our c cannot be positive, in which case c has to be negative, and so such a sequence exists. So one thing I'll note about this problem is that it says prove there exists a sequence. Doesn't necessarily mean you actually have to construct the sequence. You just have to demonstrate why a sequence that diverges, that doesn't satisfy this condition here, this c equals lim what am I saying? Yes, this being positive, why that gives us a contradiction. Okay, so for the last problem, I will show you. This was on the January 2021 real analysis qualifier. I believe it was the first problem past the theorem. I don't count the theorem. So remember, the qualifier is always theorem and then 4 problems. So if you ignore the theorem and just count the 4 problems, this was the first of the 4. So what does it say? We have a measure space. It's finite. We assume that En are measurable for every n, and we want to prove the following. If the sum of measures of En is infinity, then the sum of the intersections, the measure of the intersections, for I strictly less than j, is also infinite. So this problem was given to us as a, homework problem. Like the qualifier was given and then everyone failed it. And then he decided to give it to us as a homework problem to do on our own. And the solution that I've written up here is my own solution. I came up with this 100% by myself. And unfortunately, I did not get to present it to class that day. Someone else did. And his solution was way shorter than mine. I was amazed at just how much he was able to condense it. Because here, it takes up like an entire page here. But I'm going to present the problem that I worked on because I'm proud of it, because it demonstrated that I was able to actually do one of these problems. So what does it say? Well, I busted up into 2 cases. The first case is pretty easy. If En are pairwise almost everywhere disjoint, meaning that they only agree on a set of measures 0, then you know that the sum of the measures of En has to be bounded above by the measure of x, which is finite. Which gives us a contradiction for the second part here, because if that's finite, then we definitely don't have this part here. So we know that they have to overlap somewhere. So we know that the measures of the intersections is positive, and we want to proceed by contradiction. So the contradiction is, we have this being divergent, but we assume that this is convergent. So suppose that this sum is equal to m, and we define mk to be the sum of the measures of ek intersect j, where k is some fixed positive integer, and j can run over integers larger than k. So if k is equal to 10, And then j is 11, 12, 13, 14, 15, so on and so forth. And then we can see that the sum m here has to be the sum over all of these mk's. So I just split it up into different pieces. Now, because this series is absolutely convergent, because these mk's are positive, I can write the following line. I define the measure of E1. So what's E1 here? Oh, I know what E1 is. So E1 is that very first set that shows up in this sequence here. So the measure of E1 has to be less than or equal to the M1, which is this guy. So K here would be equal to 1 for M1. But then I'm only interested in the measure of E1, so I need to take out everything else that's not an E1, excuse me, that I don't want to count twice. So I have M1 plus measure of E1 plus the stuff I don't want to count twice. And then I define this set here, this set difference. I'm going to call that E tilde 1. So this is M1 plus the measure of E tilde 1. And in general, the case we have is that the measure of EK is less than or equal to MK plus the measure of EK plus the stuff that we don't want to count twice. And these sets are going to be called E tilde K. Now, notice that these E tildes are necessarily pairwise disjoint. That comes from how we define them, and it's pretty easy to see if you draw a picture. And I didn't draw the picture on here because I ran out of space. But it's not too difficult to see why those E tildes have to be disjoint from one another. It really just kind of comes from definition. So because they're pairwise disjoint, we know that the measure of all these EKs added together has to be bounded above by the sum of the measures of MK. But that is defined where? Here. So I have that bounded above by the measure of M, which I apparently did not write here. How naughty of me. Here, we'll use a pencil. Why not? Measure of M. Plus the measure of X. But the measure of M is finite from assumption, and the measure of X is also finite from assumption, and the sum of two finite numbers is finite. So we know that the measure of EK, the sum of measures EK has to be finite. But that contradicts our original hypothesis. So we get a contradiction. And that's what we have. Overall, I like this problem, although it took me a while to complete it. I think I worked on this problem for like a week before I got to the answer. And the sad part is, when I did it the first time, this sentence here, notice that E tilde ends are pairwise disjoint. I did not see that at first, and that's where I got stuck. And then I went to my instructor for help, and I basically presented everything here that I just showed you until I got to this part right here. So everything that my hand is covering, I didn't have. So I just showed him this part. And he immediately saw this part, and I told him I'm stuck. And he goes, you'll see it eventually. So he didn't actually tell me how to fix it. And then I called my friend on the phone who went through the master's program with me. He also has a master's in math. I was telling him about the problem, and we were just talking about nothing. I was just doodling off to the side while we were in conversation. And then I just saw it, and I told him about it on the phone that evening. And he goes, I think you did get it. So, and then unfortunately, again, I didn't get to present it, but I did go back to my instructor and say, hey, those E tildes were disjoint, were they? He goes, yeah, they were. It's frustrating sometimes studying math. So, but anyway, it's a good problem. I like it. This one's a bit easier, although I don't know sure if I could come up with it by myself. And this one, I think, needs more detail. But overall, I picked 3 relatively short problems to go over. So anyway, relatively short video. I mean, 20 minutes is short for me, I guess. So let me know what you think in the comments.